So hello and welcome back. Let's do a state estimation example based upon Bayes filters. So let's suppose that we have a robot that uses a camera to estimate the state of a door and whether it's open or closed, and we're going to represent that measurement by Z. And the door can only be completely open or completely closed. And the state of the door can only be changed by the robot's manipulator. And initially, the robot does not know the state of the door, so we'll give it a 50-50 chance that it's either open or closed. And then at time t=1, the robot takes no control action, but senses an open door. What is the posterior belief or the state estimation at t=1 and t=2? We're going to do this assuming the robot takes no action, and we'll also look at what happens if the robot does take an action. So because we don't know the initial state of the door, we will call that belief x0 equals open, 0.5, and the belief x0 equals closed, also 0.5. So first, let's define some of the conditional probabilities, for example, for the robot sensor, which is our camera in this case. And we are going to assume that the camera is noisy, therefore it will not sense the door perfectly. So the robot sensors are relatively reliable at detecting a closed door. So we will give the probability that it senses an open door when the door is actually closed, 0.2, or that it senses a closed door when the door is actually closed, as 0.8. And when the door is open, the robot sensor has a little bit more error. It doesn't work quite as well. So the probability of sensing an open door when it's actually open is only 0.6, but the probability of sensing a closed door when the door is actually open is 0.4. So then let's look at our conditional probabilities for the manipulator pushing the door open. So if the door is open, we want to say with 100% certainty the door will open. So the probability that the state is open after a push and an initial open door is 1, whereas the probability that the door is closed if the robot pushed and it was initially open is going to be a 0. It does not work quite as well if it was closed and the robot gives it a push. So if the door is initially closed and the robot pushes, the probability that it will now be open is 0.8, whereas if it was closed and the robot pushed and it's still closed, has a probability of 0.2. So now let's look at the probability of the manipulator doing nothing. So the robot has encountered a door, it sensed a door, but the manipulator does not do any changes to the world. If it chooses to do nothing, as you can expect, we would expect there to be no change to the world. So if the door is open, it will remain open. If the door is closed, it will remain closed. So these probabilities are represented as the probability that it was open, the robot did nothing, and it's still open is a 1, 0 otherwise, or the probability that the door was closed, the robot did nothing, and it is still closed is 1 or a 0 otherwise. So now let's look at what state estimation looks like if the robot does nothing. The belief at time t=1 is given by the following formula. The belief x1, and that bar over the top means that this is our belief without considering sensor measurements. It's the summation of all of the initial states, the probability of x1 given the control at 1 and the initial state x0 times the belief of x0. Or in terms of do nothing, we could write this as the probability of x1 given that the control input is do nothing and the initial state is open with a belief that the initial state is open, plus the probability of a control of doing nothing given an initial state, a closed door, and the belief of the door being closed. So if we then input the values that we have for this, we will see that the probability or the belief that x1 is open after the robot does nothing is given by the same formula we had on the previous page. But now if we put in the values for that, we get 1 times 0.5 plus 0 times 0.5 equals 0.5. And this makes sense. So if we had a 50-50 belief of the door being open or closed before the robot does nothing, we still have a 50% probability that the door is open, which is consistent and makes sense because the robot has not done anything to change the world. Similarly, if the belief at t equal 1, and we want the new state to be closed, then the belief that it is still closed would be the probability that the door is closed, the input that the robot did nothing and it was initially open, and the belief that it was open, times the probability that the door is closed, the robot's input is nothing and it was initially closed, times the belief that it's closed. And the numeric value for that is 0 times 0.5 plus 1 times 0.5, which equals 0.5. So just like what we got before, it's a 50-50 chance the door was open before the robot did nothing. It's a 50-50 chance after the robot did nothing. So now, what if we need to incorporate sensor measurements in our state estimate in order to make them more accurate? What we use here is Z1 to represent the measurement, and this would change the belief by using the following Bayes filter algorithm. So the belief of X1 is going to now be our normalizer constant eta times the probability that Z1 senses open given X1 and the belief X1 times the belief of X1. So the first thing we have to do is find the normalization constant. So find the belief that the door is open. So using the values that we had before, we will have the belief of X1 is open times the normalization constant times the probability of sensing the door is open where the state is open times the belief that the state is open. And so this is eta times 0.6 times 0.5, which is eta times 0.3. Now we need to find the belief that the door is closed. So we're going to have the belief that X1 is closed equals eta times the probability of sensing that the door is open given that the state is closed times the belief that the state is closed. And that's going to be eta times 0.2 times 0.5 or eta times 0.1. So remember what our normalization constant does is it makes sure that our probability adds to 1. All possible cases will be a 1. So the way that we calculate this is the normalizer eta is equal to 0.3 plus 0.1, and that you add those together and take the inverse, and that's 2.5. So that means now if these are our two possible probabilities, using that normalization constant to scale them, we make sure that it sums to 1. So the state estimation at t equal 1 is find the belief that the door is open. So we now know that that's going to be 2.5 times the 0.3 that we had before. So there's a 0.75 belief that the door is open. And that the door is closed is 2.5 times 0.1. So there's a 0.25 belief that the door is closed. So now, what if we want to do time 2? And for time 2, we have the following. Assume that now instead of doing nothing, the robot actually pushes the door instead of doing nothing and then measures that the door is open. So we once again are going to incorporate our control input, our measurement to determine our new state estimation. So our belief at X2 that the door is open would now be 1 times 0.75 plus 0.8.25. Notice that this is iterative, so it's building on the values we had before. And that's now 0.95 confidence that the door is open. And the belief that the door is closed would be 0 times 0.75 plus 0.2 times 0.25 or 0.05. So then the belief with the incorporation of the sensor data is 0.6 times 0.95 times eta, which is approximately 0.983. And the belief that the door is closed is eta times 0.2 times 0.05, which is approximately 0.017. So now the robot believes that the door is open with a 0.983 probability, which is much better than what we got before. So it's a matter of, do you want to take the chance of the robot driving forward and possibly damaging itself or the door? Or is that enough of a confidence for the robot to say the door is most likely open, I can now enter that space? So this concludes our example of state estimation using Bayes filter. Please watch it more than once, and I hope you're getting it. Take lots of great notes. And I've enjoyed having you, and have a robotastic day.